Good day, everybody. So today I want to look at an interesting function that's continuous at every irrational number, but discontinuous at every rational number. So that's kind of paradoxical, but it's what we will have happen. And to see that, we need to know our definition of continuity, and that involves definition of a limit. So let's start with this. Hopefully you've seen it before. Otherwise, it's going to be a lot to absorb. But we say the limit as x approaches x naught of f of x is L for some real number L if for every epsilon greater than 0, there's a delta greater than 0, so that absolute value of f of x minus L will be less than epsilon if x minus x naught in absolute value is less than delta. And we don't worry about what happens at x naught, so we've got this bigger than 0. So x not equal to x naught, but for every other x that's very close to x naught, we have to be close to what our limit is supposed to be, L. Okay, so there's some number L, and I will always be as close as you want me to be to that limit L. For every x, I can find an interval where I'm always, every x value is very close to L. So that's kind of what it means. And then for continuity, f is continuous if it's defined to be what its limit is. The limit exists and f equals its limit. So before we get to the crazy function, we'll start with a very nice function, f of x equals x squared, and we'll show it's continuous at x naught for every x naught. So proof, give me an x naught, so let x naught be given, and then given epsilon greater than 0, we're going to set delta to be the minimum of 1, and then this fraction epsilon over 2 absolute value of x naught plus 1. Basically, I want to be sure I'm always within 1 of x naught. So most likely, we always picture epsilon being very small, like 0.0001, getting smaller. But just to be rigorous here, the most delta could be is 1. So I will always be within 1 of x naught. And so that would mean the absolute value of x plus the absolute value of x naught is going to be less than 2 times x naught plus 1. So I just want to force that to happen. All right, so then we'll show the obvious, that the limit as x goes to x naught of x squared is x naught squared. So if x minus x naught is less than delta, then of course x is within this interval of x naught minus 1 and x naught plus 1. So forth. But what we really want is what's going to happen to f of x minus x naught squared. So I'm claiming x naught squared is the limit. Right? X naught's a fixed value, so x naught squared is a fixed number as well. Well, f of x is x squared, and this factors x minus x naught times x naught, well, x plus x naught, and I wrote it in the wrong order, which I corrected down here. But anyway, so it's the absolute value of this factor here, and the absolute value of a product is the product of the absolute values. So that's x minus x naught times x plus x naught. I wrote it back in the right order here. And now I'm only looking at x's within delta of x naught. So x minus x naught in absolute value is less than delta. Right? So if x minus x naught is less than delta, then this product is less than delta times this. And then, of course, the absolute value of a sum is less than or equal to the sum of the absolute values there. If they're both positive, it's the same, or if they're both negative. But if one were positive, one were negative, they might be different. But you get the less than or equal to take care of that. And the absolute value of x, though, is less than or equal to absolute value of x naught plus 1. So I can put that there. And so that's just 2 times absolute value of x naught plus 1. And how did I define delta? Go back up here. It's the min of 1 in this, so it'll be less than this quantity. So I replace delta. So it's actually strictly less than, but whatever. Put less than or equal to. Replace delta with this, and then these cancel, so that equals epsilon. So that proves that f of x minus x naught squared is going to be less than epsilon if x minus x naught is less than delta based on how I defined it. And again, I did the scratch work first and kind of see what I needed. So you didn't see the figuring out what I would need for delta ahead of time, but I won't go through that. And if we want to picture it, if you're new to this, again, for f of x equals x squared, let me actually do an actual number, say x naught is 3. So I'll show the limit exists at x naught equals 3. And I'll do it with a specific epsilon, namely 0.01, so 1 over 100. Then using delta this way, with epsilon 0.01, x naught 3, you get 0.01 over 7. So we can show that f of x minus 3 squared, 9, will be less than 0.01. Right? So you give me the epsilon first, and then I'll find the interval so that I'm always within 0.01 of 3 squared, 9. And let's look at a picture of that first. So there's the parabola, and we're investigating continuity at this point 3, 9, and here it is. So my delta is right here, 3 minus 0.01 over 7, 3 plus 0.01 over 7. So in other words, 3 plus or minus delta. So for all the x's in that interval, the y's are going to be inside. So here's what I graphed. The parabola now looks like a line, and then I graphed these two lines. So all the function values are within 0.01 of 9. Cut back a little bit. So here's all the x's that are within delta of 3, and here's all the values that are within epsilon of 9. And you can see all my function values are within epsilon of 9 when the x's are within delta of 3. So that's pictorially what happens. I don't know if I want to show it any more mathematically. It's kind of here, but let's get to the crazy function. So here's the interesting function. F of x is 7 for any irrational number, and then 7 plus 1 over q if x is rational. So in other words, x equals p over q for integers p and q in lowest terms. And we always take q to be positive, so p could be positive or negative, but x equals p over q in lowest terms. And this is kind of a famous example, although they usually just use 0 and 1 over q. I decided to shift it up 7 because otherwise there's too many zeros, so I wanted to get rid of that. So, but if this is a popular example, that's usually 0 for x irrational and then just 1 over q for x rational, but I made it 7 and 7 plus 1 over q. Just a shift of the popular example. Right, so first I'm going to show the limit as x approaches root 2 of f of x equals 7. And of course, f of root 2 is 7. Root 2 is irrational. So f will be continuous at root 2. Right, so the proof, let epsilon be given. For example, epsilon could be 1 over 100, 0.01. Now what we need to note is there are only finitely many rational numbers whose denominator, q, is smaller than 100. And q is always positive. Put that in there. that are within 1 of root 2, right? I mean, there'd be infinitely many rationals, but if I want to be within 1 of root 2, there's only finitely many. And I listed too many. I don't know why, I couldn't help it. So in the end, they're a subset of, well, 0 is already farther away than 1, so like I shouldn't have listed it. But 1, and then 2 over 1. Now 3 over 1 would be too big, so I didn't list that. 1/2, 3/2, and that's it for fractions whose denominator is 1 or 2. If I go to fractions whose denominator is 3, I've got 1/3, 2/3. I'm not going to repeat fractions, like 3/3 is 1. That wouldn't be in lowest term, so I shouldn't list it. 4/3, 5/3, 6/3 is 2, it's already listed. 7/3, and then 8/3 is too big. And then with denominator 4, 1/4, actually that's more than 1 away, but I listed it anyway. 1/3 is more than 1 away from root 2 as well. But anyway, so it's a subset of this list. 3/4, 5/4, 7/4, 9/4. That's all the fractions in lowest form that are within 1 of root 2 and have denominator 4. And you just keep going. Just increase the denominator 1 more and then list them and so on. Eventually you'll get to denominator 100, and then 43 over 100 is within 1. 42 over 100 is not in lowest terms, and 41 over 100 is more than 1 away. So that time I didn't list it. So 43 over 100 is the first fraction that's within 1 of root 2, denominator 100. Then 44 over 100 is not in lowest terms. 45, 46 over 100, not in lowest terms. 47 over 100 be the next one. And so on until you get to 241 over 100. And then that would be it. That's the complete list. A little too much, but of all fractions that are within 1 of root 2 whose denominator is 100 or less. So there's only finitely many. And if there's only finitely many, then there's always a minimum distance, right? I want to find which number is closest to root 2. It turns out 99 over 70 is the one closest to root 2. And there's ways to find it, but we won't go into that. Anyway, and here's 99 over 70's decimal approximation. So that's the best rational approximation of root 2 among all fractions whose denominator is less than or equal to 100. If you were to compare them, I mean, obviously some of these are really far. I could have, going 1 away is quite a bit. So if I look at how far away 99 over 70 is from root 2, I mean, there's the decimal approximation for both. You can use a calculator. So it's roughly that far away from root 2. So if I make delta smaller than this number, say just 0.00007, then if any rational number is closer to root 2 than that number, it must have denominator bigger than 100. Because any rational number that's closer than this to root 2 can't be in this list, and this lists them all whose denominator is 100 or less. So there are rational numbers closer to root 2 than this, but they all have denominator bigger than 100. Okay, so in other words, repeat myself, if delta is equal to that, then x minus root 2 less than delta means, so f of x minus 7, it's going to be exactly 7 minus 7, which is 0 if x is irrational. But if x is not irrational, so if x equals p over q, it's a p over q, and you're within delta of root 2, then f of x minus 7 is f of p over q minus 7, but what's f of p over q? It's 7 plus 1 over q. And that'll be 7's cancel. That's just the absolute value of 1 over q, but I'm taking q to be positive, so it'll be 1 over q. But q has to be bigger than 100, so 1 over q is less than 1 over 100, or epsilon. And that can be generalized, right? So for every epsilon greater than 0, we can find a delta greater than 0, so that f of x minus 7 is less than epsilon whenever x minus root 2 is less than delta. And you just kind of do the same thing. Given the epsilon greater than 0, here I did it with 10 to the n. So find the minimum n so that 1 over 10 to the n is less than epsilon. Then there would only be finitely many fractions p over q within 1 of root 2 to have denominator q smaller than 10 to the n. And I decided to call that list set e sub n with this exponent. So that the list of all those fractions, you call that like e sub n. And then if you set delta equal to half of the minimum, so whichever fraction is closest to root 2, set delta to be half that distance. Okay, so out of all those fractions, it's a big number of fractions perhaps, but it's a finite list. One of them will be closest to root 2. Whichever one's closest, let's set delta to be half how close it was. And so if that's delta, then now if I have x minus root 2 less than delta, again, f of x minus 7 is 7 minus 7, or 0, if x is irrational. And f of x minus 7 will be f of p over q minus 7, but that's 7 plus 1 over q minus 7, which is 1 over q. But that's going to be less than 1 over 10 to the n, which is less than epsilon, for rational x. So in this interval, I always have f of x minus 7 less than epsilon. It's either equal to 0, which of course is less than epsilon, or it's equal to 1 over q, which will be less than 1 over 10 to the n less than epsilon. So as stated, the limit as x goes to root 2 of f of x is 7. F of root 2 is 7, so f is continuous at root 2. And actually what we did works for every real number as far as the limit goes. For any number, the limit as x goes to that number will be 7. Because no matter what, for every epsilon greater than 0, you can always find a delta greater than 0, so that f of x minus 7 is less than epsilon whenever x minus c is less than delta. It mimics what we did with the root 2. Well, here I didn't do 10 to the n, I just did a step function. So let m equal 1 over epsilon, and then make it a little bigger. So 1 over epsilon, if epsilon is really small, 1 over epsilon is big. I added 1, and then just take the integer that's above that. So this floor function. So the greatest integer, actually it's the least integer that's greater than or equal to 1 over epsilon plus 1. So I should have put in here, in the end, 1 over m will then be less than epsilon. Right. M has to be an integer, so you kind of just want m to be 1 over epsilon. If m is 1 over epsilon, then 1 over m is epsilon. But I need it to be an integer, and I want it to be a less than, so I just made it a little bigger, and then I just made sure it was an integer, biggest integer, the smallest integer that's bigger than this value, bigger than or equal to. But anyway, so I've got this m, right? So you give me the epsilon first, I can find this integer m, and now again there'll only be finitely many rational numbers within 1 of c whose denominator is smaller than m. Right? Once m is fixed, you're down to finite. I mean, you could have infinitely many p, so I had to have p within something. I just chose 1 of c. So that makes there's only finitely many fractions with that denominator within 1 of c. This denominator is smaller. So again, that's a list of fractions. It's a finite list. So let delta, here I wrote it in words, be the distance that real number is to the closest one in that list, and then divided by 2, just to make sure. Right. So out of that finite list, one of them is the closest. Find that distance. One of them is closest to c. Find that distance. Divide by 2. Then all the rest are now outside this interval. So if x minus c is less than this delta, I'll have f of x minus 7. 7 will be 7 minus 7 if x is irrational. And if x is not irrational, then f of x minus 7 will be 7 plus 1 over q minus 7, or 1 over q. But 1 over q is going to be less than or equal to 1 over m, because I'm only looking at fractions whose denominator is less than or equal to m. And 1 over m will be less than epsilon. So the limit as x goes to c of f of x is 7 for every value of c. I should state that separately here. Well, I stated it first. So the limit as x goes to c of f of x is 7 for every real number. And of course, if c is irrational, then the limit equals the value of the function, 7. But if x is rational, if c equals p over q in lowest terms, then the limit is 7, but the value of the function is 7 plus 1 over q. Now they're different by 1 over q, which might be small, but they're still different. So the limit is 7 for every real number, and that's the value of the function at the irrationals, but it's not the value of the function at the rationals. So the function is discontinuous at every rational number, but continuous at every irrational number. And of course, the rationals are dense. You know, between any two numbers, there's always a rational number. So that's kind of hard to picture. Anyway, that's the function. Hope you enjoyed that. Thanks, and have a good rest of your day.